Welcome everyone. My name is Hidde and I'll be presenting the work I have conducted together with Kevin and Herman on restricted weight minimum dilation spanners on 3 points. In this work we're interested in spanners, specifically those in the real plane. As already mentioned in the title, we are investigating spanners on point sets of size 3. Therefore, to keep it interesting, we allow additional Steiner points. Now, before we define our problem exactly, we first introduce two notions. Firstly, the weight of a spanner is the sum of the Euclidean lengths of all the edges in the spanner. Secondly, the dilation between 2 points is the ratio between the shortest distance over the spanner between the points and the Euclidean distance between the points. Thus, in the example on the right, the dilation between the two top points is 1, as the Euclidean distance is equal to the shortest distance over the spanner. For the other two pairs of points, the dilation is greater than 1, as the Euclidean distance is smaller than the distance over the spanner. We investigate spanners which are restricted in weight and have the lowest maximum dilation. We thus have a maximum weight, which we refer to as the budget, from which we want to construct a spanner which has the lowest maximum dilation over all pairs of points in the point set. We can now formalize the problem. Given a point set P and a maximum weight L, find the spanner G such that the weight of G is at most L and the maximum dilation over all pairs of points in P is minimal. Now, while solutions can be found using convex optimization, we are interested in the structure of these optimal solutions. We study the structure for general point sets of size 3, as well as the cases where these point sets form isosceles and equilateral triangles. The smallest budget that allows for a spanner will logically result in the minimum Steiner tree, as seen here on the left. For very large budgets, on the other hand, naturally the complete graph is optimal, as this gives the minimum obtainable maximum dilation of 1. The interesting area thus lies between these two extremes, which is exactly what we investigate in this work. First, we will dive into the general topology for any optimal spanner for a point set consisting of 3 points. To prove which topology is optimal, we use a number of properties. The most important property we exploit concerns the statement on this slide. For an optimal spanner, the maximum dilation equals 1, or the weight is maximal. For any budget surpassing the weight of the complete graph, the weight of course does not have to be maximal, that is equaling the budget, for the spanner to be optimal, as the complete graph suffices in this regard. For the case where the budget is lower than the weight of the complete graph, any remaining budget can be split over all the paths with maximum dilation to decrease their dilation, leading to a more optimal spanner. Using this fact, we built the topology from the ground up. After drawing an arbitrary path between two vertices in the point set, the other paths can be constructed following a number of further properties. Trivially, the path should be injective, and thus not self-intersect. Furthermore, if two paths share 2 points, their respective subpaths between these points coincide. Finally, all paths are contained in the convex hull of the original point set. Using these properties, we derive this general topology. As a path's Euclidean distance, and therefore its dilation, is minimal if it consists of straight line segments, we arrive at this general shape. We thus observe that an optimal spanner consists of an inner triangle connected to the outer triangle consisting of the original vertices. Note here that the inner triangle can be degenerate. In fact, that is how the spanner starts off in the minimum Steiner tree configuration. The question that then comes up is whether optimal spanners for larger budgets can still contain degenerate inner triangles. Before we can answer that question, we first introduce further supporting statements. For the Steiner points forming the inner triangle, we introduce this notation, where A' is the point at which the paths between A and B and A and C split. Now let us consider the case where one of the paths has a lower dilation than the maximum dilation of the spanner. For example, the path from A to C. If the inner triangle is not degenerate, we can move the corresponding segment in the inner triangle parallelly inwards to decrease the overall weight of the spanner, while not increasing the length of the other paths. As such, using the previously mentioned result that the weight should be maximal, we conclude that this spanner is not optimal. We thus conclude that the following statement must hold. In an optimal spanner, A', B', and C' coincide, or the dilations are all equal. The point where the transition between a Steiner tree and the spanner containing an inner triangle occurs has been coined as the dilation center by David Epstein. Denoted by X star, it is the Steiner point minimizing the maximum dilation of the Steiner tree. Notably, it has been entered into the Encyclopedia of Triangle Centers as X3513. The spanner, consisting of the segments connecting the dilation center to the outer vertices, is referred to as the dilation star. To formalize the statement I just made on the dilation center being the transitional point, we introduce the statement shown on the slide. For any weight L, such that L is at least the weight of the minimum Steiner tree and at most the weight of the dilation star, any optimal spanner satisfies A', B', and C' coinciding. First, we show that the dilation star is optimal for the corresponding weight. Let us assume that it is not optimal and that there does exist a spanner, G, with at most the same weight and a smaller maximum dilation. By its definition, the dilation star is optimal amongst spanners with A', B', and C' coinciding. Thus, A', B', and C' must be distinct in G. Now let us consider the location of the dilation center. If it is located inside the inner triangle, using the fact that the sum of the lengths of the segments connecting the vertices of a triangle to any point in the interior of the triangle is smaller than the sum of the lengths of the triangle's edges, we can conclude that G must have a larger weight than the dilation star, which is a contradiction. The dilation center must thus lie outside or on the boundary of the inner triangle. But then, the path of G enclosing the dilation center will be longer than the corresponding path in the dilation star. As such, the maximum dilation of G will be higher, again resulting in a contradiction. We can thus conclude that the dilation star is optimal for the corresponding weight. Next, we consider a budget smaller than the weight of the dilation star. Here we will only provide a rough sketch of the proof. Again, assume that there exists an optimal spanner G with A', B', and C' distinct. As the weight of G is lower and as the dilation star is optimal, the maximum dilation of G must be at least that of the dilation star. However, as A', B', and C' are distinct, the dilations of all paths must be equal. We can show that among all spanners with equal dilation, the dilation star is of minimal weight. This follows from the fact that in the dilation star, all segments are used in exactly two paths, whereas any spanner containing a non-degenerate inner triangle contains segments which are used in only a single path. Therefore, G cannot exist. Thus, we conclude that for any weight L, such that L is at least the weight of the minimum Steiner tree and at most the weight of the dilation star, any optimal spanner satisfies that A', B', and C' coincide. There are thus two phases of growth in the development of the spanner. In the first phase, the spanner has a degenerate triangle as its center, which moves from the Fermat point to the dilation center. The spanner thus transforms from the minimum Steiner tree into the dilation star. In the second phase, the spanner contains a non-degenerate inner triangle, which grows until the spanner equals the complete graph. If we consider the more restricted case where the given point set forms an isosceles triangle, we can make a further statement. Namely, for an optimal spanner for such a problem, if A', B', and C' coincide, this point lies on the perpendicular bisector of the base of the isosceles triangle. This result follows from straightforward geometric analysis, which we will not get into here. Together with the previous result, this statement characterizes the optimal spanners for isosceles triangles for a budget of at most the weight of the dilation star. When we restrict the case further to where the given point set forms an equilateral triangle, we can show more elaborate results. To that purpose, we first introduce a general geometric statement. If for a triangle the sum of the lengths of the triangle's edges is given, the sum of the distances from the vertices to the Fermat point is maximal for an equilateral triangle. This statement also follows from straightforward geometric analysis. We will use this statement in the proof for the optimal spanner for an equilateral triangle for any budget. Let us consider two spanners. On the left, we have an arbitrary spanner adhering to the general shape as introduced earlier. On the right, we have our supposed optimal spanner. It consists of an equilateral inner triangle centered within the outer triangle with its vertices on the bisectors of the angles of the outer triangle. The spanner on the right is constructed such that the weight of the inner triangle is equal to the weight of the inner triangle of the spanner on the left. We suppose only the left spanner to be optimal. Important to note is that as the outer triangle is equilateral, and as the dilation is equal if A', B', and C' don't coincide, the pairwise paths between the points must be equal in length. This trivially also holds for the spanner on the right. Thus, using that the segments forming the inner triangle are only used in a single path, whereas the connecting segments are used in two paths each, we can directly relate the weight of these elements to the dilation. We then consider the following modification. For both spanners, we replace the inner triangle by its minimum Steiner tree. As such, the vertices A', B', and C' are directly connected to the Fermat point of the inner triangle. Because we suppose the original left spanner to be optimal, either its maximum dilation must be smaller than that of the original right spanner, or it must have a lower weight. Using that the inner triangles were of equal weight, both statements are equivalent to the sum of the lengths of the connecting segments of the left spanner having to be smaller than that of the right spanner. The modified left spanner will have a weight of at least the minimum Steiner tree of triangle ABC. The modified right spanner, on the other hand, is the minimum Steiner tree. Thus, the weight of the modified left spanner equals at least the weight of the modified right spanner. If we combine that with the general geometric statement that for the weight of a triangle given, the sum of distances from the vertices to the Fermat point is maximal for an equilateral triangle, we observe that the sum of the lengths of the connecting segments of the left spanner must be larger, unless the inner triangle was centered and equilateral. Therefore, it can only be optimal if it is equal to the spanner on the right. Thus, as for an equilateral triangle the Fermat point and the dilation center coincide, we conclude that for the given point set forming an equilateral triangle, the inner triangle is equilateral and centered in the outer triangle, with its vertices on the bisectors of the angles of the outer triangle. From simple geometric analysis, one can then determine the exact location of these Steiner points. Thus, in our work, we have first provided the general topology of optimal spanners for any 3 points. Next, we have characterized the optimal spanner for a maximum budget of at most the weight of the dilation star for the point set forming an isosceles triangle. Finally, we have shown the optimal configuration for the point set forming an equilateral triangle for any maximum weight. From our simulations, we have made a few more observations. Our first conjecture, based on this experimental work, is that for isosceles triangles, the optimal spanner is symmetric in the perpendicular bisector of the base of the triangle. While we have proven this for the case where the spanner only contains a single Steiner point, we have not been able to generalize this to the case where the spanner contains a non-degenerate inner triangle. Secondly, we conjecture that for isosceles triangles with an angle at the apex of at most 120 degrees, the connecting segments are of non-zero length, unless there is sufficient budget for the complete graph. Thirdly, for general triangles, we conjecture that in decreasing the budget to the weight of the dilation star, in the limit, the inner triangle is equilateral. And finally, also for general triangles, we conjecture that if the connecting segments are of non-zero length, they meet in a single point. Apart from investigating these conjectures, future work could focus on different point sets. The first extension would be to consider the problem for more points, for example for quadrilaterals and pentagons. Furthermore, one could investigate point sets in different coordinate spaces, potentially of higher dimension. Other objective functions than maximum dilation are also interesting cases to study. For instance, one could look into using the diameter or the total pairwise distance as the objective function. Experimental work based on convex optimization has already been conducted in 2 master theses by Koerts and Verstegen, which could provide insight into the structure of solutions for larger point sets. With that, we would like to conclude this talk and thank you for your interest.